All right. Hi, everyone. Welcome back to another Talk Math with your friends. It is my pleasure today to introduce today's speaker, Dr. Juliette Bruce. Dr. Bruce is a postdoc with UC Berkeley and MSRI, and today she will be speaking about moduli spaces of a curve. So everyone, please join me in welcoming Dr. Bruce.
Thank you so much, everyone, for the introduction, and I am glad to see some people I already know in the audience, and for everyone who I don't know, it's nice to meet you, and I hope to be your friends already, if not by the end of the talk. And so as said, I'm Juliette Bruce. I'm a postdoc at UC Berkeley. I'm also at MSRI. Before moving to the Bay Area, I grew up and did my graduate work in the Midwest, the Great Lakes region, so I'm a recent West Coast transplant. And I'm going to talk about graphs, curves, cones, moduli spaces, dark matter, and many other things. But before I get to the math, I think there are a few acknowledgements that are important for me to make. Where I work and live occupies the ancestral and current homeland of the Mokemo Ohlone tribe and other familial descendants of the sovereign Verona Band of Alameda County. Black and Indigenous lives matter. Further, where I work and live is only a few miles away from the site of Compton's cafeteria, where 51 years ago, in the face of transphobia, police violence, and state violence, one of the first actions in the modern LGBTQ rights movement occurred, led by Black, Brown, and Indigenous trans women. Black and Indigenous LGBTQ's life matter. With those important acknowledgements said, I'm going to transition to the math, but I also want to hold for a moment if anyone needs space to process, to give everyone a chance to kind of hold for a moment before we move on. Okay. So shifting to the math, I said I'm going to be talking about the moduli space of curves. And if you've never heard of what curves are, or you've never heard what a moduli space is, please don't fret. The goal of this talk is to try to introduce these things in as down-to-earth way as possible. But before we even get there, I want to kind of give a prologue about a fact that I just think is really, really cool. So I think I called this the prologue. And it's about graphs. And so for me, right, a graph is just a collection of vertices or nodes connected with some edges. I'm not going to label my edges. I'm not going to put directions on them. I really only want to think about connected graphs. So here's a nice graph. You might also have a graph that looks something like this. Or maybe even something with more vertices. So maybe I want to do something with a pentagon. Okay, let's try to clean this up a bit. So here, I have these outside 5 vertices and then a central one, and I am connecting them up with some edges. Will these notes be available after the webinar? Potentially. We'll see how my notes actually look in the hindsight of me giving this talk, but potentially. So I have to introduce 3 terms for graphs, right? So the first is that we say a graph is trivalent. Just means that every vertex has at least 3 edges, right? So for example, which of these graphs is trivalent? Let's, I guess, give them names even. This is A, this is B, and this is C. So which of A, B, and C is trivalent? Audience participation, friends. Say it aloud or type it in the chat. Whoever wants to shout it.
A couple of us are doing the hand symbol for B.
Oh, thank you. So B is definitely trivalent. C is also trivalent, right? Every vertex here has degree at least 3. The outside ones have degree 3, and this inner one has degree 5. Similarly, every vertex in B has 3 edges, which means it's degree 3. And here we don't have 3 it's not trivalent because this vertex, this vertex, this vertex have degree 2, and this one has degree 1. Are there configurations that are not allowed in the graph, like two edges connecting the same two vertices? So we are not, for the time being, I don't think I want to allow multiple edges, and I don't think I want to allow self-loops. So I'm not going to allow things like this or things like this, although certainly I think those come up very naturally in later on, potentially. And I agree, the Dipper graph is great, which is maybe this graph here. It reminds me of the show Gravity Falls, which I very much like. So the next notion is genus. So the genus of a graph is just the number of holes in the graph. Which we can also think about just being the dimension, if you want to be fancy, of the first homology group. If I think about G being some topological space in the plane, but right, just more down to earth, we might say the genus of this graph is 1 because there's exactly one hole here. The genus here is 3 because I have 1, 2, 3, and here it is 5. 1, 2, 3, 4, 5. The genus is sometimes hard to define and hard to see. How do we define it if it's not planar? That's a great question. And I think the easiest way to define it when it's not planar is we have to then use the definition of homology. Alternatively, we could try to use other kind of more ad hoc definitions coming from combinatorial formulas for the genus, coming from edges and vertices, things like Euler's formula. But really, I think when you're non-planar, you're beating about the bush of how should I define homology in some sense. So we have trivalent, we have genus, and the last notion we need for this prologue is that an automorphism, the automorphisms of a graph G are just going to be the permutations of the vertices that preserve the edge structure. So things that permute the vertices and take edges to edges. And so what would the as an example, if I look at this graph down here, the pentagon graph, the wheel graph, right? What type of automorphisms can I have? Well, essentially, I can move the pentagon any way I want, but I can't move that central vertex because the central vertex has too many edges going in. So you could show that the automorphism group of C is going to be the dihedral group on 2 times 5 elements, so it has size 10. Right? You can kind of imagine you can rotate the picture however you want, or flip the picture around any natural thing, and you can get here. Here you could see that you can in fact move any vertex to any other because they all look the same. In fact, this is the complete graph, and so this exactly says the automorphism group is in fact a symmetric group on 3 letters or vertices. It has degree 6. Okay.
4? Is it 4 things?
Oh, 4 things. Yeah.
It's 4. Yeah.
Thank you. I totally. See, this is why I said I'll see how this talk goes before I share my notes where I write down S3 when I want to write down S4, which has size 24. Okay, so here's that's the basic setup, and now here is the thing that I think is an amazing fact that I'm going to attribute to Kontsevich in 1993, although maybe it was known by others in other forms. But so here's the thing. I'm going to take a sum of -1 to the number of edges of my graph G. And then what am I summing? I'm going to sum 1 over the number of automorphisms of G. So you give me a graph G, I count the automorphisms, I do I put a negative sign depending on the parity of the number of edges. And what am I summing over? Well, it's going to be graphs G, where the genus of G is equal to G, and these are connected and trivalent. So I'm summing over connected trivalent graphs with 3 holes, and I'm summing, kind of counting the automorphisms in some reciprocal way. And the amazing fact is that there is in fact a closed formula for this sum, which I find to be incredible. Namely, it's BG, which I'll say what that is in a minute, divided by G times G minus 1. And what is BG here? BG is the Bernoulli number. So these are the Bernoulli numbers, which if you take them and put them into a series and do e to the t divided by e to the t minus 1, these are exactly the coefficients of the Taylor expansion of this function. So bk, in this case, is an amazing audience member, but is also the term that appears in the series expansion of t divided by e to the t minus 1. And so you got bk times t to the k divided by k factorial. So this is maybe the definition of Bernoulli numbers for some. And so B2, for example, would be 1/6. B3 is 0. B4 is negative 1/30. So they're somewhat sporadic. But amazingly, right, this formula is, I mean, it's a weird thing to imagine writing down, but you can write it down and actually get a very nice closed formula. And in fact, I think this isn't something I'll touch on, but somehow often it's a theme in algebra that somehow counting by 1 over the automorphisms is the right thing to do in life. Obvious question, what the hell? I mean, yeah, I don't have a good explanation for why this should be this. It touches, so the proofs I know of this fact are entirely kind of non-obvious to me, at least. The most down-to-earth proof somehow says, oh, I want to count 1 over the automorphisms. This is somehow equivalent maybe to counting other combinatorial objects that come up. And we can do these combinatorial objects via some generating functionality. And then if you are a physicist, you might immediately recognize this framework of having to do something with Feynman diagrams and magic that I don't understand. But so I think of this fact as amazing in part because I have no idea in my heart of hearts where it comes from. But for example, right, this tells us that when G equals 2, this sum is going to be 1/12. When G equals 3, it's 0, which, I mean, that's entirely non-obvious even to me. And when G equals 4, it's negative 130, negative 1 over 360. So I don't know. This is just an amazing fact that I think is cool and will come up later in the talk. So let's put this aside in a box for a little bit of time and move on. And so the main subject of the show is the moduli space of curves. And so there are 2 things we have to define, right? Like I have to explain to you what a moduli space should be, and also what that's supposed to be a different color, what a curve should be. And we're going to start by what is a moduli space. And so here is a question for the audience. What is a moduli space? Does anyone want to give an answer? Or when someone says it, does your eyes just glaze over and you say, oh, no?
For me, it's a geometric object whose points classify some other set of geometric objects.
Yeah, right. So I think that was exactly the answer I wrote down on my paper, is that a moduli space is just some broad type of word that just means a space whose points parameterize, so maybe are in one-to-one correspondence, maybe, you know, has some other nice properties, some given collection of geometric objects. And what type of geometric objects? Maybe it's curves, maybe it's points, maybe it's lines, surfaces, donuts, triangles. You would give a set of geometric objects. Is finite required? Finite on the objects or finite on the space? On the object, no. On the space, it's often very difficult in some sense to determine whether you can have a nice finite, maybe in dimension or in other nice senses, whether you can have a nice finite moduli space. Maybe by finite you mean compact, like that's kind of like a finite thing in Rn. And by space, you know, I said the word space here. What do we mean by that? Well, it could be topological, it could be a vector space, it could be a manifold, it could have other structure, algebraic. You know, it's just kind of a general framework in the world. And so the example that I want to spend some time on is something that almost ties in to something we were talking about before, which is the moduli space of non-vertical lines in R2. So I want to find some space, again, squashy word, that parameterizes, also squashy word, the set of non-vertical lines in R2. So I have on the one hand, I have non-vertical lines, L inside of R2, and I want to somehow find a way to parameterize these. And this ties in to, I think, the conversation beforehand when someone said, geometry, that's just algebra. So how can we parameterize a line in R2? And it's not a vertical line. What do I have to do? mx plus b, I'm seeing m comma b. And so I'm seeing a lot of, right? So the point is that a line L is exactly the set of points x comma y, where y equals mx plus b for a, you know, if I have fixed an m and a b, is exactly things of this form. And so what we can think about this as being is, well, if I want to specify a line, you have to tell me m and b. So I can think about the space of lines as being an R2 consisting of the coordinates m, which gives me the slope, and b, which gives me the intercept. And we kind of, at some points in our education, learn this fact, and we don't think about the fact that there's actually something very deep going on here. Namely that you can take a line in space and represent it by its slope and intercept is something very deep. And it actually gets at kind of a lot of amazing facts about lines. So what would this moduli space look like? Well, I have an R2. So here's my R2. And, you know, here are maybe my axes. And different points inside of here correspond to different types of lines. So for example, if I look at points along the line I'm dashing now, right? These are all lines of the form y equals mx. They don't have any b if I make this my m and this my b axis, right? And so somehow we can see that the set of lines without intercepts seem closer than other lines. And likewise, maybe the lines on the other axis represent things of the form y equals b. And again, we can kind of somehow see that the lines that don't, the vertical lines, or sorry, the horizontal lines form kind of nice families. Those points in the moduli space are close. It's not like you have one line that has slope 0 here and another line that has slope 0 way far away. No, they're kind of packed together somehow in some natural family. And so the question is, well, why might you care about moduli spaces? Why would you ever think about this? And the answer is, instead of giving you a concrete answer, I'm going to instead ask a different question, which is, suppose I take a point. So let P comma P1 comma P2 be a point in R2. And then I can ask for the set, which I'm going to call HP1, P2. Maybe bad notation, but it's going to be, I want it to be the set of M comma B, where the point P1 comma P2 is on y equals mx plus b. Okay, so this is kind of weird. So I have two different R2s going on, right? I have an R2 where the point P1, P2 lives, right? And I take that point and I want to say, what are all the possible lines that contain the point P1, P2 in the plane? But instead of thinking about this as being lines in the plane where the point P1, P2 lives, I want to think about what it looks like as a subset of our auxiliary moduli P2, R2, where my coordinates are M and B. So if I gave you a point P1 and P2, how can you find the set of all M and B that such that P1, P2 lie on that line?
Point slope formula line instead or something like that?
Well, I mean, right, like essentially, right? So if you can think of a point slope formula, or you plug it in, right? If P1, P2 is on the line mx plus b equals y, then when I plug in P1 for x and P2 for y, the equation better hold. That's what it means to be on the line. So this is exactly the set of m comma b where P1 comma m plus b equals P2. To be even more concrete, for example, right, if I make these numbers 3 and 5, well, this is just the set of MB such that 3P or 3M plus B equals 5, which is another way of writing a line in M and B, right? So the point is this gives me a line. So in this case, right, the set of points that lie here is a line, HP1, P2. And so you could do the same thing for a different point, right? If you take Q1, Q2 in R2, you can ask the same question. What is the set of points that such that of what is the set of lines such that Q1, Q2 lie on that line? Well, HQ1, Q2 is again just going to be the set of M comma B, where MQ1 plus B equals Q2. This is also a line in the plane, so we get a different line in the plane. And what do we know about two lines in the plane?
They meet in a point.
Yeah, two general lines in the plane meet at a single point. Assume, you know, we throw out the exceptional cases. And so what does this tell us? Well, this says HP1, P2, the set of lines containing the point P1, P2 intersect the set of lines containing the point Q1, Q2 is a single point. And a single point on the MB, on the plane, on the moduli space says it's a single line that contains both P1, P2 and Q1, Q2. So what we just, so what this statement is equivalent to, right, is that in general, you know, 2 points determine a unique line. And so somehow we exactly have the fact we can kind of recover a very geometric fact, namely that 2 points determine a line, from looking at this moduli space. And this is kind of a general theme that if you want to understand how things behave, sometimes it's natural to study everything all at once, because sometimes you want to study how things vary in formulas. It would be easier if the two R2s had different names. I agree completely. Sorry.
You have the XY plane and the
Yeah.
MB plane.
Yeah,
Yeah.
so you have the XY plane and the MB plane. And beautifully in the plane, the moduli space just happens to be the space itself almost. There's some sort of duality you might have heard about from kind of geometry, where you can take lines and points match up. But yeah, it also makes it confusing. Moduli space has a similar geometry. Also, good question. Amazing idea is that somehow often if you have objects with a certain structure, maybe they're vector spaces, maybe they're topological spaces, maybe they're algebraic spaces, the moduli space of such things often has the similar structure. So here we had an R2, we had an R2 on the similar thing, and that's pretty amazing. So a more complicated example that I'll just start to sketch, and maybe we'll come back to if we have time, is the moduli space of triangles up to similarity. Okay, but actually before I get there, I should say, here I had the word non-vertical, and you might ask yourself what happens when you drop that condition and I allow vertical lines. And if you think about this story, you'll start to be led to beautiful things like projective space and real projective space and spheres, and the story can just unfold. And so I'll leave that to you. So I now have to think about the space of all triangles up to similarity. Okay, and this one's a little more complicated. So let me get us started. So I have the plane where everything lives. Okay, doesn't want to make that a straight line. Oh, well. And so if I gave you a triangle and I'm allowed to only consider it up to similarity, what I could do is I could first shrink it so the smallest side has length 1. Does everyone agree I could do that? So I could shrink it so it has smallest side length 1, and then I could take all my triangles in the plane and move their shortest side so that the shortest side of my triangle was pinned down here, right? So here is my shortest side. It's in blue. It's length 1. This is the shortest side. Let me put it. Okay, so I pinned down my shortest side and 2 of my points of my triangle. So how do I determine a triangle now?
A third point more than 1 unit.
Yeah. So I have to give you a third point somewhere else on the plane because, right, a triangle is specified by 3 points in the plane. And I've told you 2 of them, so I just have to put the third one somewhere. But the rule is, right, that I can't be within distance 1 of either of these 2 points, right? So somehow, see, here's where my drawing comes, my ability to draw circles just fails me. So here, right, so here are 2 balls of radius 1, right? And so to specify a triangle, I just have to pick whose shortest side is this blue side. I have to specify anything outside the red circles. Okay. But there's a big but, right? That I only want to think about triangles up to similarity. And so some of the points I pick, right, are going to result in similar triangles, right? So for example, if I pick this point here, nope, let me pick. If I pick this point here, and I pick the point here, I claim you get similar triangles. I claim that this triangle, actually, let me do it in red. I claim that this triangle here is going to be similar to this triangle here. And can anyone tell me why?
Congruent via the reflection.
Yeah, it's congruent via the reflection. So in some sense, right, anytime I flip over the y-axis, I get similar triangles. So I can throw out of my moduli space everything over here because they're similar to things in the right two quadrants, right? I claim, for a similar reason, that if you look at the line, let me give it a different color. If I look at this line here, then anything beneath this line, a same distance, will give you similar triangles. So if that's not how you draw a triangle at all. So if I take this triangle and I take this triangle, they're similar because I can reflect over this line here. And so for the same reason, I can throw out everything below this line. Are we allowed to degenerate triangles? Seems like we should throw out the y-axis too. Great question. And I think that's just a matter of definition that I am going to be agnostic on. Can I throw out the y-axis? If I don't want degenerate triangles, right, because triangles up here would look like lines, I should definitely throw it out. If you want to allow degenerate triangles, let's keep them in. I leave it to you to decide what the best definition of triangle is for your case. But now we have this moduli. I claim this is essentially it, right? So that, in fact, all the rest of this is essentially the moduli space of triangles up to similarity. There aren't really any more similarities you can take into account. And if you look at this, you can start to see some nice things, right? So, for example, here's a fun line in my space. This pink line now represents all of the right triangles, because if I take a point on the pink line, I get a right triangle. So this pink line is right triangles. Beneath the right line, well, down here I'm going to get acute triangles. And up here, I'm going to get obtuse triangles. You might, if you think about it, you can also figure out where the isosceles triangles live with various bases. Some of them are going to live along here, some will live other places. And so really you can somehow see that this picture is telling you that, well, if you imagine taking an acute triangle and moving it around in some ways that it became obtuse, you could kind of imagine that at some point, if you moved it well, you'd have to pass through a right triangle. That somehow if you kind of move it in a continuous way, you couldn't go from an acute to an obtuse triangle without going through a right triangle. And that's because somehow you can't get around this line. You have to cross this line. So you can kind of start to see that this moduli space is actually going to tell you something about triangles. Okay? So that's a whirlwind tour of moduli spaces. And so the second question was, what is a curve? And so when I talk about a curve, I normally mean a smooth algebraic curve over the complex numbers, but an easier, some more maybe down to earth, if we want to say that, I guess, definition might be that it's a Riemann surface, which I don't think necessarily helps, but we can go even further to saying that this is just a compact, connected complex, you know, we can squint about what that means, surface. And so what do I just mean? It's going to be some nice compact surface in some space. It's going to have some holes. It can't have any pointy bits. It can't go down to, I mean, I can imagine drawing surfaces. I can't imagine, I feel like the name Riemann surface just makes me think of, I don't know, whatever Bernard Riemann looked like. I don't actually know what a picture of him is, so. Right, but I can imagine drawing surfaces, right? So for example, what's a very nice surface that I like is, you know, here's a surface, here's a sphere. Maybe you want a donut in the morning. That's a nice surface. And, you know, maybe you want a donut that has more holes, something like a weird apple fritter or something that has a bunch of holes, right? So these are surfaces. These are curves to algebraic geometers because they have real dimension 2, but over the complex numbers, they're dimension 1. Well, it is almost lunchtime depending on where you are, so that makes sense to be hungry. So I also have to talk about genus, and genus is, again, just the number of holes. So here, genus 0, 1 hole means genus 1, and 4 holes just means genus 4. Yes, and Dave points out that my sweeping the notion of being complex forces everything to be orientable and nice and great, but, you know, we can sweep that under the rug as friends and vacuum up later. And then,
Yeah. I mean, it's probably the more important thing to point out is that the complex structure means that there's, like, you know, unlike in topology, there's more than one curve
yes.
of genus 1, say, or genus 2.
Yes.
Yeah.
Yeah. So, yeah, since we're thinking about these as complex things, right? We care about exactly, we can't squash them however we like. We care about what their actual complex structure is, so what they actually look like as complex manifolds or as, you know, algebraic curves. So a little more complicated, but, you know, we can picture what these types of things might look like. And then the definition is that MGN is not a movie studio, but is instead the moduli space of genus G curves with n marked points modulo subnotion of isomorphism, which I'm not going to get into the technical details. So by marked points, I just mean I'm going to pick some points on my surfaces and say those are the points I want to say. Maybe we're putting sprinkles on our donuts, or, you know, little bits of apple on our fritter. And isomorphism kind of means you can take one to the other in a nice, smooth, complex way, and the points on your one marked surface go to the marked points on the other. Okay. So just to judge time, should I end at 20 or 30? What's the protocol?
We're having some discussion, so you can go close to 30, but
Okay.
if you like.
So let's do an example of one of these things, just so we can say there's a nice example. Although I will punt a lot of the example to the exercises. So as exercises, so we're going to look at genus 0 with 3 marked points. So when we're looking at things of genus 0, we're essentially, yes, looking at a bowling ball, because the genus 0 thing looks exactly like the sphere. In fact, there's a much stronger result. The sphere in algebraic geometry land gets the name P1 for the projective line, because we're thinking about complex dimension 1, so it's 2 dimensions over the real numbers. But an amazing fact, which fun exercise that actually takes quite a bit of work. So probably a bad exercise to think too hard about on your own, although it's still fun, is that every genus 0 Riemann surface, so every genus 0 curve is isomorphic to P1. So it's honest to God a sphere with a given complex structure. There's only one of them. And so now if I'm thinking about these curves, I can think about one sphere. And the question is just, how can I move my 3 points on the bowling ball around? So there are no sizes of bowling balls here. Everyone gets the standard issue bowling ball. And we just have to figure out how many different places we can put the holes up to automorphism. And the second exercise is that, and this one is maybe a little more doable, is that the automorphism of the Riemann sphere is exactly given by the projective general linear group of 2 by 2 matrices over C, which is a fancy way of saying that it's given by fractional linear transformations. Z goes to AZ plus B divided by CZ plus D. That's kind of the automorphisms of the complex plane, which are the same as automorphisms of the Riemann sphere. But the important thing about this group is that it's 3 transitive. So it takes any 3 points you like to any other 3 points you like. So in some sense, up to the automorphisms, it doesn't matter where you put your bowling ball finger holes. You can put them over here or over here. There's always an action of this group that will take wherever you put your finger holes before to where you want them, which is pretty good, that you can put your finger holes in your bowling ball wherever you would like. Yeah, don't do this to your hand. That would hurt. But what this essentially means, right, is that if we take any given points, P1, P2, and P3 on the Riemann sphere, we can map them to the points 0, 1, and infinity. And what this essentially means is that there's really only one choice of points up to the action of this group. In particular, it tells us that M03 is exactly 1 point. There's only one Riemann surface of genus 0, and there's only up to the action of automorphisms 1 point to put your finger holes. Using this, you can also work out with the action of what the moduli space is with 4 marked points. That's not 4, this is 4. 4 marked points on the Riemann sphere is using a similar thing. But sadly, in general, for moderately large G, say G bigger than 24, maybe 25, there is no nice description of these moduli spaces in general. They get very, very complicated very quickly. And so here, I should briefly mention that there's a lot that goes into this definition. I've claimed that this is what it is, but saying what something is and saying it exists, maybe those are different things, maybe not. I don't know what your philosophical predilections are, but I will say that Riemann in 1857 used the term moduli to describe this thing and even computed its dimension in some sense. But it took until 1965, so over 100 years in some sense, for someone, namely Mumford, to construct this space in a nice algebraic way that was satisfying, I think, to modern algebraic geometers. Although certainly people along the way, like Grothendieck and Vey and many others, some with sordid histories, will not be who I won't name, were able to construct this space in similar way in other contexts. So with the last few minutes, I want to end by just mentioning a cool fact, I think. So I said that these spaces, these MGNs, these moduli spaces, get complicated pretty quickly, but they're still topological spaces. And so that means I can look at the cohomology of them. I can write down the homology groups of them, and I can write down the alternating sum of the homology groups, which is called the Euler characteristic. Put a different way, right? If I imagine with graphs, we have Euler's formula, faces, I don't know, faces plus edges minus vertices. I'm never sure. I'm not going to get the sign right here. You can do that. You could do that in general for this space as well. And it's a theorem of Harrier and Zagier from 1986 that if you look at the Euler characteristic of this space Mg, so I now don't have any marked points, and here I need to be put a little tiny decoration to denote that this is maybe the orbital Euler characteristic, but again, let's sweep that under the rug and we'll clean it up afterwards after the party is done. So this is some number, and what number is this? Well, it's Bg divided by 4 times G minus 1. And lo and behold, that formula up to the factor of 4 here looks very, very similar to the formula we had at the beginning, which also is just amazing in some ways. So if you squint at their proof, you can maybe see a connection, but I certainly wasn't, excuse me, expressed clearly in their proof what this connection. And the fact that Koncevich's formula came out in 93 suggests that it wasn't maybe people hadn't thought about graphs in this way. And in fact, I personally am not 100% sure if you can go from one to the other concretely. I'd have to think much more difficultly about that. But I think this is an amazing kind of at least numerical coincidence, but this also has some interesting implications that I'll just end by saying, which is that this implies that, well, up to a sign, the normal Euler characteristic of Mg is asymptotically of the size g to the 2g. So the Euler characteristic is growing super exponentially, g to the 2g, which means that as soon as g is somewhat big, we're going to have an absolute ton of cohomology, right? There's a lot of cohomology happening here. And this is even after taking into account that some of it might get canceled. Definitely, one thing you can think about is taking the graph and puffing it up into a Riemann surface, and that is definitely a great idea and is a good connection between these two things, and that's, as Brian is saying, BK is saying, tropicalize everything. But I think I'll just end by saying an amazing, I think, mystery in some ways that will explain the last thing that I'll just say very vaguely is that until recently, let me put it this way, the amount of cohomology of Mg we knew was on the order of something like a constant to root g. So even sub-exponential, or yeah, I guess exponential, sub-exponential, I'm not sure what the right terminology there, but it's definitely much, much smaller than g to the 2g, right? And so what am I hinting at here for people who might want to Google later? What I'm saying here is what was the cohomology we knew about before. This is things coming from the stable, something called the stable cohomology of Mg, which is work of Madsen and Weiss, and also, yeah, so what do we mean by the cohomology we know? I'm saying there's something called the stable cohomology of Mg, I'm not going to define it, and it's a theorem of Madsen and Weiss that that thing exists, And I'm saying that if you look at the dimension of the stable cohomology, it is roughly growing in the order of constant to root g. I should mention that very recently, recent work of Melody Chan, Sam Payne, and Soren Galatis produces more cohomology of roughly the order, let's call it beta to the g, so we get honest to goodness exponential quantities of cohomology for mg. And their methods really kind of leverage a connection between the moduli space of curves and graphs, which has been suggested in the chat. Namely, you imagine puffing up your graph, right? So you imagine somehow if I take a Riemann surface like this, I should be able to associate it to some type of graph, namely the graph that looks like this. And how can I do that? Well, I either imagine puffing up the edges, kind of putting a straw in there and blowing it up and inflating everything, or you kind of imagine, I don't know, something like this. I'm drawing it quite poorly, but somehow you kind of can imagine these things being related to each other. And so at this point, I think I'll stop. Thank you for being my friend today and talking math with me and listening. So I'll turn it over to questions. And yeah.
Excellent. Thank you. Please join me in thanking Juliette. One of the reasons I was thinking about tropical stuff at the beginning is that the trivalent, that the higher degree ones are like degenerate curves. And so is that degeneration, does that make sense in terms of this formula? My dissertation work was the tropical curves, moduli space of tropical curves, and Hurwitz numbers. So I was thinking that the automorphisms might be like a ramified cover, and that you might be sort of summing over all the degenerate types of things, but it seems like it's different than that.
So I think that's a great question, and I think I am not sure of the answer, and I think that there are other people in here, yourself included, who might be more experts on this than myself. But certainly one approach, right, would be to degenerate everything to the boundary of the closure event, the compactification of mg, where you're allowed to include stable things, which would correspond to trivalent graphs, and then ask about if you can compute it in terms of the degenerate boundary. And certainly that will tell you some cohomological information. It's unclear to me whether you can compute the full orbifold Euler characteristic from this sort of thing. On the other hand, the proof given in the 80s somehow kind of, I don't know, I'm not an expert on the details of it, but isn't too horrible, and somehow uses kind of explicit, like if you look at the paper, you'll see a lot of pretty pictures of CW complexes and things that feels reminiscent. So I'm not sure. And I think there was a question in the chat that maybe I didn't answer. Josh, what do you mean by amount? That's a good question. I'm saying by amount, I'm being very hand-wavy and soft and squishy and vague. I'm saying maybe a precise way to say this is you can look at package all the cohomology into one ring. Then you can look at the graded pieces, and you can ask what is the dimension of the graded pieces up to some given degree. And so I'm talking about dimension. And so for example, here, right, this is kind of an alternating sum of dimensions. The stable cohomology range is going to exactly say, looking at all the stable cohomology up to a certain degree, 3/2 g minus 1, I think. You can look at the dimension of that. Here, I'm looking at the dimension of one particular cohomology group. Yeah, and so that's what I roughly mean.
Great. We have time for maybe one more question.
Yeah, I have a question. Do you think Okay, so if I understand correctly, the result of was it Kunsevich is it doesn't fall. You don't. He doesn't use Harzaghier to prove that. But let's imagine that there's like some world in which you could do that. Is there any reason to expect this factor of 4?
That's a great question, and I don't know. I think I think if you could explain the factor of 4, I feel like you might be able to intuit where what the proof might be somehow, maybe, right? Like if you said, oh, these differ by a factor of 4, the 4 is because you're over counting by this, right? You might see, oh, exactly what the connection is, but I'm not sure. I should say I'm definitely not a expert on any of this, but I think it's really cool, and I like moduli spaces, and I think the fact of Kunsevich is just a really cool one that I stumbled upon sometime last year.
It's honestly surprising to me that you can't derive the one formula from the other.
I mean, you might be.
Maybe
I'm not going to say you can't. But...
well, I don't mean. I mean that hasn't been written down.
Yeah.
Anyway, very nice talk. Thank you.
So we have our last little announcement here. Please join us next week. Abigail Burnett is going to be talking to us about knot diagrams in 3 dimensions. Abigail, I think you're here. Would you like to give us a 30-second preview?
Sure. So apologies, my camera is not working with me today, but 30-second preview. Knot theory appears in artwork around the world throughout history, and I turned it into sculptures, and you'll hear a lot about my artistic and mathematical journey, as well as a lot about historical stories of knots appearing both in our math textbooks and in our lives. So see you next week.
Excellent, thank you. And finally, please everyone unmute and join me one more time in thanking Juliette for an awesome talk.
Hey!
And thank you all for being here and engaging. Thank you for being my friends. So I'll clap for you now.
I love that.